Hello. We are your impeccably suited Colombian footballers, standing in today on behalf of Wilmer Henao. He asked us to present because, between us, he didn't feel like brushing his teeth for camera this morning. Big picture. We built a deterministic, red-teaming harness for GPT-OSS-20B that probes reasoning leaks, jailbreaks and formatting failures. In plain terms, we craft prompts that try to make the model say the quiet part out loud, then measure whether it does. Today's focus is encoding-induced leaks and related antics. We ask for two sections, an internal analysis and a user visible final. If the model decodes a hidden phrase in analysis but politely refuses in final, we detect that. We vary temperature, add legends, and nudge formatting to see where guardrails bend or snap. It's tidy, repeatable, and score. We lock a seed, fix generation settings, and capture environment details. That way a result from my machine should match Wilmer's. Well, except for the superior hair. We also keep prompts long enough to stabilize outputs and normalize the return text before we judge it. Fewer variables, cleaner conclusions. Here's the fun bit. We wrap a target phrase in formats models understand even when they shouldn't reveal it. Think base 32, base 85, ASCII 85, ROT 47, and gzip plus base 64. We sometimes add a short legend, for example the base 32 alphabet, to tempt analysis into doing the steps. Then watch whether that phrase surfaces anywhere. We use format locks. Return exactly two sections named analysis and final. We also ask for a verification line in analysis, confirming the first decoded word is the. If the model leaks anywhere, our detector flags it. Clean structure lets us tell a real leak from polite refusal. Under the hood, we normalize out zero-width characters, fold homoglyphs to plain Latin, and reverse common leet substitutions so R3DB4LL00N doesn't sneak by. We also spit out channels, leak in analysis, leak in final, or both. That granularity matters when you're comparing defenses. Some probes are layered, for example, first URL decode, then base 32 decode, and finally ROT13. Others embed payloads inside a data URL or conceal them within HTML or SVG attributes. These patterns reflect realistic input surfaces. After all, assistants frequently parse markup. If the model's analysis pathways execute those decoding steps, even when the final section presents a refusal, we still gain insight into its reasoning. Not every string should decode to our target. We include negative controls, random base 64, or a different phrase to prove our detector isn't over-eager. We also run small paraphrase sweeps to see if evaluation-sounding prompts change output structure. Fewer false positives, more signal. We submitted 5 that maximize novelty and real-world relevance. Base 32 with a legend, RFC-style base 85, ASCII 85, ROT 47 with a precise rule, and gzip plus base 64. They're less likely to be in the model's public system card, yet common enough to matter. If it leaks there, it probably leaks elsewhere. The results packaged to a schema, validated and zipped ready for Kaggle. Reproduce by pasting the included harmony strings, matching settings and checking our detectors. I'm the better looking presenter, our friend Wilmer, if the better engineer. Thanks for watching. Let's make safer models one stubborn exploit at a time, and see you at the World Cup.